Mukund, are you ready?
Anytime.
Okay, so let me introduce you and then we start. Hi everyone, welcome to HoloTube after the Easter break. We're very happy to have Mukund Rangamani, who's agreed to give a talk even at 7 a.m. in California, if I understand correctly. And he's gonna tell us about effective field theory and diffusion from holography. Please go ahead.
Thanks. So indeed, I'll talk to you today about some work I've been doing in the last maybe year and a half. But primarily in this, mostly we'll focus on this paper. So this was done with my friend Logan Igon from ICTS, his student Chandan Jana in a paper we started this in a paper from last April. And the paper that I mentioned was with Loga, Joel Ghosh, Siddharth Prabhu, Loga student Akhil Shivkumar and Vishal. There's some ongoing work with our postdocs, Temple Hay and Julio Virueta, and some combination of these people. So let me start with a broad brush motivation. And since you folks are all quite familiar with the technical aspects of some of the stuff I'm going to tell you, I'll try to give a slightly technical flavor to the talk. Recent times, I've been mostly talking about the sort of implications of this from a broader perspective. Okay, so there are two questions I'm after, and one is in the discussion, which is, I'll phrase it as this, sort of, how do you phrase, how does one construct effective field theories for open quantum systems? And here, let me explain what I mean. You can think of an open quantum system as follows. So we could just do it physically. Think of some plasma that's sitting in some lab. And this is your sort of, we'll think of this plasma as in a slightly different way from where you're used to. We'll think of it as an environment. And we'll stick a probe, which we'll think of as a system. And we'll consider integrating out the plasma and try to write down an effective action for the probe. Now, a priori, this sounds like a story that you could have said for any system, and it's something that you might have said, okay, did Ken Wilson solve this 50 years ago because he told us how to write down effective couplings in effective field theory weighted by coefficients that we would determine by recourse to microscopics. There's a catch, and the catch here is that the plasma plus system evolves unitarily. The plasma plus probe undergoes unitary evolution, but the probe by itself does not. And this problem is interesting for many reasons. You could phrase this in the language of entanglement buildup in the probe, in terms of or in terms of directly saying that we have an effective non-unitary Lindbladian evolution for the probe, which you would like to phrase in terms of what the effective Lindblad couplings are. Okay, and this is not a new problem. This problem has been around for I don't know, 60 years. The first people to tackle this problem were Feynman and Vernon in the 1960s, who gave a very nice path integral description of what the effective couplings of the probe should be. And the way they phrased it was that the effective action of the probe, because now the probe is not in a pure state, but in a density matrix, should be thought of as an action for the Kets, an action for the brass, plus a coupling between Kets and brass. Okay, so I'm just thinking of the probe system as some quantum state, which is given by some density matrix. And I'm using the fact that density matrix is an operator, which has both a Ket piece and a bra piece. And so I should keep track of both of them independently. And the relative sign is simply because bras evolve anti-unitarily relative to cats. And the statement I wanted was basically saying what governs, what unitarity constraints constrain SIF in effective. Okay. And I've been interested in this problem for a few years now. And one such problem you can think of, while I phrase this in the context of a probe coupling to a plasma, we could just as well think of this as the effective description of real-time hydrodynamics, where you would want to write down a hydrodynamic stress tensor and its associated fluctuations, both of which would come out of this effective action for the probe. Okay. So I'll come back to that because hydrodynamics is going to be the context I'm primarily going to be discussing today, but this is the broader context of the problem I'm interested in. The classic examples of this, which have been well studied in literature, and you can find very good discussions of them in the quantum mechanical setting, primarily starting with Feynman Vernon, a few years, maybe a decade or two later, Caldera and Leggett solved this problem for quantum Brownian motion by thinking of the plasma as a bath of harmonic oscillators at finite temperature and the probe as a single harmonic oscillator. Okay, so you put a harmonic oscillator in a bath of harmonic oscillators and then integrate out the bath and see what the effective action of this single oscillator is. And this problem leads to an effective description of quantum Brownian motion. So you get Langevin dynamics for the oscillator, plus fluctuations coming from the fact that the bath has fluctuations. One way to say what these unitarity constraints are is the following. If you think of this plasma as a thermal system, then in the plasma, you have not just the fact that the plasma, if you probe the plasma, it's like you hit the plasma with an external source, then you see retarded response, but associated with every retarded response is a corresponding fluctuation, stochastic and quantum. Okay, so this we know from the early story of Brownian motion and the Einstein-Somolchowski relation, which tells you how the sort of the origins of dissipation and fluctuations being the same give you the Einstein relation between fluctuations and dissipation. In modern language, I would say this is like a KMS condition in thermal correlators. So this effective action that I'm trying to construct should know about such conditions. And the question really becomes, how do I incorporate this from first principles in the problem? So as I said, for quantum mechanics, this problem is very well studied. As far as I know, there is no well-developed technology to study this problem in quantum field theory. The various models give you various seeds of confusion. So for example, various people have tried in the past to do denormalization of an open quantum system in just phi cube in this phi to the fourth theory coupled to scalar fields and integrate out one of them. And you encounter various puzzles. So I'll refer you to a paper by Logan Agam and his collaborators who worked this out recently in the context of just what I said, scalar field theories. But their example turned out to be quite special. There are subtleties with other generalizing it to other systems. So that motivates me to look for a paradigm where at least I know the answers are sensible. And the paradigm I'm going to borrow from is the one that we are all familiar with, and that one that seems to give us good answers is the paradigm of holography. And I'll tell you why in time to come. So to summarize, I need sort of open EFTs in quantum field theory is not fully developed. But there's a second catch about this problem, which is what happens when, so maybe I'll just say we are looking for a paradigm. And we'll use holography as a crutch. And second is I'm concerned with systems, or as I said, plasmas or environments with long-term memory. So they have moduli, or if you like, they just have very long-lived modes that don't disappear. So when you try to integrate out the plasma, your effective action for the probe system retains non-local effects coming from the fact that you've integrated out very massless modes. And here, the paradigm I want you to keep in mind is think of hydrodynamic plasmas with conservation laws, which give long-lived hydromodes. Sound/shear modes. So all of you are familiar with this. We've all sort of played with this in the context of holography. I want to tell you something slightly different from what I will recover many things that every one of you has seen, but I'll also tell you something slightly different in terms of how this calculation is organized. It's going to be slightly different in practice from what is usually computed. There's a corollary to this, which is in holography, these hydromodes, are long-lived quasi-normal modes. And we would like to know an effective action governing their dynamics. Maybe I'll be very clear here. They're real-time dynamics because they don't exist on shell in Euclidean time. Is tantamount, I claim, to telling you what coupling is going to S-probe into the effective action. Why? The real-time dynamics of these quasi-normal modes of these hydrodynamic quasi-normal modes has both, as I said, retarded response this gives you the hydro poles, the diffusion/sound poles in the correlators. And then there should be an associated Hawking fluctuations, which are stochastic fluctuations of the fact that as the black hole emits spontaneous simulated radiation and relaxes back, as it relaxes back, it emits simulated radiation, which has to be accounted for in the Hawking quantum. These are 1/n suppressed, of course, in the large N theory, but we'd like to understand how to incorporate them in an effective action. And we have to, it's non-optional, simply because the influence space cares about relations between of that kind. The detailed balance in equilibrium tells you the rate at which the Hawking quanta are emitted relative to what the retarded response is. And if you like, one can phrase this problem as saying, compute the gray body factors of Hawking radiation for long-lived quasi-normal modes. And what I don't want to do is just compute the Green's functions, which is the computation which pioneered the whole field going back to Polycostos and Starinets almost 20 years ago. But rather, I want to package this into an effective action, and I want to know what to compute. Okay. So let me say what has been done and why this is slightly different. So what has been done is many calculations of correlation functions. Mostly 2-point functions, though there's some very nice piece of work by Dana Warman, Peter Arnold, and collaborators on computing 3-point functions, and I'll come back to that later. And there is a converse story which never really computed, this is in the linearized theory. This calculation is linear in amplitude. Because you just look at fluctuations of the black hole and study the quasinormal modes. And then there's a completely different story which limits to this in the linear approximation, which is the fluid gravity correspondence, which is nonlinear in amplitude. It computes the effective 1-point function of the currents in the presence of sources. So you can use it to recover the Green's functions if you like. But it works with equations of motion. So it doesn't compute. So in some sense, it's on shell. It's on shell for most of the discussion, but some set of equations are still off shell because the hydro equations are not solved in the fluid gravity correspondence. And this is going to be a difference from what we're going to do. We're going to try to actually solve all the equations as much as we can and compute a boundary effective action, which will be appropriately the generating function of correlation functions a la GKPW for real-time physics in a black hole background. Okay, so punchline is really this. So we'll have a formalism to compute using holography, a boundary action, a boundary effective. Let me say an effective action for bulk fluctuations. Which encodes both retarded and response and its associated fluctuations. So that's the broad brush goal of this program. And we've succeeded in computing this, giving a dictionary for probe fields which don't have long-lived quasinormal modes at arbitrary Green's for arbitrary correlation functions. That was the paper from last April. And we have now a story to tell for how to what to compute and how to keep track of the moduli in the case when you have long-lived quasinormal modes. Okay. So what I'll try to tell you is I'll tell you the story in 3 pieces. is setting up the bulk geometry and the computation. Second, I'll tell you an effective designer models, an effective set of designer models to understand long-lived quasi-normal modes. And finally, I'll tell you a bit about some general results. And primarily here, I'll just talk about diffusion. I won't talk about sound. Sound more or less works the same way. It's just a bit more technically involved. Okay, any questions so far about the broad brush story? Great. Okay, so although I phrased the problem in terms of open quantum systems, for now we can just forget about open quantum systems and let's just focus on a single problem. We want to compute correlators in the boundary field theory at real time, and we want to ask how to do these calculations. So I'll remind you a few things about real-time calculations at finite temperature, and then say what the geometry I should compute it in is. So if I'm trying to compute thermal correlators, then I should be computing them on the following contour to keep track of certain causal ordering. So the contour runs in some complex time space. It has a excursion. So I'm trying to compute correlators of the following form. Where T1 and T2 are operators are inserted on the contour. Real time runs this way. Imaginary time runs up. And the contour starts, let's say, at 0, has an I epsilon excursion, minus I epsilon excursion, and then ends up on the thermal density matrix with an I beta. I should probably remove an I epsilon if I've written an I epsilon excursion out in the far future. The correlators you compute are contour ordered, and if you repurpose them, they will give you, these will give you both the causal objects, like the retarded response, and the fluctuations which are in the anti-commutator. And the KMS relation relates these two. For 2-point functions, there's a simple way to say what's going on. There's a single Whiteman function. And these two guys are that Whiteman function dressed up with Bose-Einstein factors. or Fermi-Dirac factors if you're talking about fermions. So those of you who played with spectral functions, the Weightman functions basically give you the spectral data, they give you spectral functions, and then you can trace them up suitably with the appropriate combination of the statistical factors, and one combination gives you the retarded response, the other combination gives you the fluctuations. And the KMS relation is a statement that they both come from the same gadget up to, and if you look at these two correlators, they're related up to a statistical factor. So, okay, so we have this gadget. We need to compute, and the same thing holds for higher point functions. Let me say a priori that the Schwinger-Keldysh correlators are not the full set of arbitrary time orderings for endpoint functions. For 2-point functions, they're everybody. All the 2-point functions can be gotten from the Schwinger-Keldysh contour. For higher point functions, you need more contours, like the out of time ordered contour for 4-point function onwards. Okay. So I will only be talking about Schwinger-Keldysh ordered correlators. I'm not going to talk about out of time ordered correlators in what I'm discussing. Very good. So now let me remind you of a piece of history, just to set the stage. Let's say we want to compute these guys in holography. We want to compute this retarded response in holography. So famously, Son and Starinets gave a very nice prescription about, again, almost 20 years ago, where they said, look, what you do is you solve the wave equation in the black hole background, in the Lorentzian black hole background, single copy, and you do the following. You impose ingoing boundary conditions, so that gives you causal ordering. It picks out the future ingoing boundary condition, picks out the retarded response. That's the right physical constraint. And then to compute the 2-point function in real time, you basically drop any horizon contribution and double up the contribution at infinity. Okay. This was a prescription they just, as far as I can understand from their discussion, they just postulated. It was motivated later by Herzog and Son by looking at the structure of the Kruskal diagram and, roughly speaking, using a thermophile double construction to motivate. Now, there's a big difference between a thermophile double contour and the Schwinger-Keldysh contour, and I will emphasize it. I've said this in many other contexts, but let me emphasize it. The thermophile double contour has an excursion by I beta over 2 here into imaginary time, and the remaining I beta over 2 is at the far past. This is fine. This is what the eternal black hole gives you from the bulk construction. But this has a problem in that it doesn't make some of the causality features, the unitarity properties of the Schwinger-Keldysh construction manifest. Okay, so I will not talk about the thermophile double contour, and so I'm not going to use their prescription as it stands. A few years after them, maybe in the mid or 10 years ago, Skenderis and Van Rijs looked at this problem again, and they said, well, the right thing to do for these kind of contours, if this is a boundary contour, what you should do is for every Lorentzian segment of the contour, like this one, you should patch in a copy of the Lorentzian solution. For every Euclidean solution of the contour, you should patch in a copy of the, for these two pieces, you patch in 2 copies of the Lorentzian solution. And for these Euclidean excursions, you patch in Euclidean geometries. And both Van Rijs actually managed to derive very nicely the ingoing boundary condition from that discussion. That's all very nice, but this was a piecewise smooth geometry. It was not quite, it was continuous. It was not obvious from their boundary condition that the geometry was C2. And so when it actually comes to solving equations beyond leading order and trying to compute on-shell actions, it's not quite clear what to do. Okay, and so when I said 3-point functions are computed by Diana Varman and co, Diana Varman and Peter Arnold and company, what they did was they cleverly used Euclidean and Lorentzian techniques to patch together to get the 3-point functions, because they were interested in getting second order transport from correlation functions, and they did this about 10 years ago. But for a long time, all of this was very frustrating to me because there was no clean GKPW like Witten diagram prescription in a single geometry that I could just use to do the computation. And this changed about 2 years ago in a very nice paper by Crossley, Glorioso, and Liu. Who, I will reinterpret their statement, who basically gave a complex geometry, which it was two-sheeted, on which one can compute and this was analyzed by Loga and friends in the context of Brownian motion, but I'll tell you how I think about this contour. This is not the pictures they drew, but this is the way I think about it. So let me take this Schwinger-Keldysh contour and turn it around its head, rotate it by 90 degrees. And to make things simpler, okay, I'm going to try to draw a complex geometry in 3 dimensions. So bear with me. You'll see what I mean, and I'll draw a Penrose diagram in a second to tell you what I'm actually doing. So this is the Schwinger-Keldysh contour, times run up, times run down. And then I'll just draw the Euclidean segment as just as a circle to indicate that in the past, I'm preparing the state from a thermal density operator. So this is just a Euclidean time evolution to prepare that state. Now, we know from Gibbons and Hawking that the saddle for the Euclidean geometry is the Euclidean cigar, the Euclidean black hole. So let me draw that. Keeping in mind that I have cut out the Euclidean black hole. I've cut out the Euclidean time evolution along a sliver of width epsilon, and then patched into Lorentzian segments. So I'll take the cigar and cut out a sliver from the top of it. That sliver has to smoothly come and hit the tip of the cigar. And then I evolve this in Lorentzian section. So I get some kind of half dome, but this is now a smooth sheet where this is two-sheeted because one sheet is the thing you're seeing, which starts at this front end of the sliver, and there's a second sheet in the back, which is just folded over. So I'm going to draw it like this. This is heuristic, but it's a good mnemonic for what's happening. A better way to say what's happening is you take the geometry of the black hole in ingoing coordinates. Okay, I'll just write some general black hole where f of r has a simple single zero at horizon, not an extremal one, so it's a non-degenerate horizon. And I'll analytically continue it to a complex two-sheeted geometry by introducing a complexified tortoise coordinate. So zeta is not the radial coordinate. So if I'd written no I beta and written this to be just 2 dvdr, this would be like the ingoing Eddington-Finkelstein coordinates for the black hole. I'm just going to take the ingoing Finkelstein coordinates and then convert r to a complex coordinate. So here's my rule for r. So r is related to zeta by the black hole function. Okay, so you standard tortoise coordinate, but with some factors of I beta or put in so that there's a monodromy of 2 pi for this zeta coordinate as I go along the horizon, go around the horizon, because f has a single zero and the residue at that pole is set by beta in the Hawking temperature. And so if you think of the zeta coordinate, zeta is double valued, and the functions we are discussing have been analytically continued in the radial coordinate by introducing a cut which runs from the horizon to infinity, and the contour that I will study the physics, the two sheets correspond to jumping this cut, where one leg of the contour, by convention, I take zeta to have real part 0. The other leg, I take the real part to be 1. See, zeta, if it weren't for my factor of I, zeta would have been purely the tortoise coordinate, okay, up to some factors of beta, which are irrelevant. So zeta is like an imaginary tortoise coordinate. So I like to call it the mock tortoise coordinate, for those of you who know the illusion. And the two branches are characterized by the real part of zeta having non-zero values, having different values. In one contour, it's 0, the other it's 1. The choice is asymmetric, but this is a nicer choice to see what happens. Important point, and the point is that this geometry is not, this Lorentzian two-sheeted Lorentzian geometry is non-singular. There is no, it goes nowhere near the black hole singularity. It doesn't need to go anywhere near the black hole singularity. In particular, if you try to draw this on a Penrose diagram, the front sheet that I've drawn here is like the future half of a black hole. It's this region, and the ingoing coordinates fall in. And there's another copy of the same, the back sheet is another copy of the same geometry. Where the time comes back out, because here time runs, the boundary runs this way, and on the back side, you see the time runs down. So on this two-sheeted geometry, this seam, there's a catch, and so I should emphasize before I mislead anyone that this is also a postulate. This is not a derived fact, but it's a postulate that we can test, and it passes all tests that we would like to throw at it with flying colors. So it's a correct postulate. These folks computed certain 2-point functions. Loga and friends had previously computed for a probe quantum mechanical system of a probe string that computed higher point functions. And in the paper I mentioned from last year, we showed that A, the GKB dictionary can be made precise in these geometries, and B, you can use it to compute arbitrary high point functions. So for the first time, we computed 3-point functions and 4-point functions from these geometries just by playing with the propagators by doing standard bulk to boundary dictionary. And the calculation is what you'd naturally expect. So for example, if you want to compute a 4-point function, you insert 4 operators on the boundary. This is a Schwinger-Keldysh ordered 4-point function. And you have bulk to boundary propagators, which you can sort of glue in maybe with 3-point vertices or 4-point vertices, depending on what the bulk dynamics is of the field to get the appropriate correlation functions. Okay, so we only did contact diagrams, but it's clear that you can do non-contact diagrams, etc., etc. There's one technical thing that some of you might appreciate. So let me tell you one thing. On this geometry, there are 2 types of bulk to boundary propagators, because there are 2 sheets. So there's one sheet where time is running up and one sheet where time is running down. So if you like, there's a time ordered propagator and an anti-time ordered propagator, or translating in bulk language, there's a ingoing propagator and an outgoing propagator. Now, there's a very nice trick to convert to, so one advantage of working with ingoing coordinates is that regularity at the horizon is manifest. Okay, so this is not true if you work in Schwarzschild coordinates where the horizon is just singular locus from coordinate point of view. But one disadvantage of working with ingoing coordinates is that time reversal is broken. Okay, because the outgoing modes are not strictly speaking regular on the future horizon, they're regular on the past horizon. But there is no past horizon in this geometry. The geometry is only confined to the future half of the Penrose diagram on both sheets. But let me show you this at the level of writing a scalar wave equation, or let me tell you something at the level of CPT transformations. There's a particular combination. So in my coordinatization of ingoing time t and, oh, terrible. I can't use t and v, so let me just use v here. So v is my bulk time coordinate. Sorry about that typo. So v is bulk time and zeta or r is basically bulk radial coordinate. Both roughly speaking thought of as complex. One way to say what I'm doing is that usually when you go from Euclidean time to Lorentzian time, you go from when you draw the Schwinger-Keldysh contour, instead of drawing a contour along the real line, you just take a contour in the complex time plane, a codimension 1 curve in the complex time plane. Now think of the TR plane and make it a copy of C2 and take a codimension 1 surface on C2, which is basically whose real sections coincide with the black hole sections. And they're glued suitably with some monodromy conditions on which respect KMS on the horizon. That's one way of saying what this geometry is. I don't know how to derive it just yet, but I'll just say for reference, for those of you interested, I have been thinking about what are the rules for generating real-time path integrals, for generating saddle points of real-time gravitational path integrals. So there's a paper I wrote a while ago with I thought Lefkowitz and Zhidong in the context of trying to derive the holographic covariant entanglement entropy formula. And more recently with Don Merrill, G, and my student, Colin Ellerin, and Don's student, Zhencheng Wang, we've been trying to come up with a prescription to think carefully about what the variational principle for real-time geometries with replicas is, and this is a problem of that kind. And one can justify to a large extent that this saddle is a saddle. I haven't been able to justify that it is the saddle. Okay, so the time reversal operation, there's a Z2 involution in this geometry, and the Z2 involution is useful. Which is the map V to I beta zeta minus V. So this is T2 minus T in Schwarzschild coordinates, but in this complexified ingoing coordinates, this is and we can say many things, but the thing I want you to want to say is that associated with this Z2 involution, you can define a derivation which is not quite Leibnizian, but you can deal with it. Are upgrades of our conjugate, our Z2 conjugate. radial derivation operators. The reason to say this is the following. Operationally, and I won't go through the details in the 20 minutes I have, but operationally, we only solve the ingoing problem. We solve for the ingoing Green's functions. This is a problem that every one of us has solved in the past. We're trying to find quasi-normal modes. The CPT transformation relates these two guys. So if you solve the ingoing Green's function, allows one to get G out by roughly G out at R omega k is e to the minus I beta zeta. No I. You can show this at the level of the wave operator, so you don't have to resolve the problem to find the outgoing Green's function once you know the ingoing Green's function. And the general Green's function is a linear combination of them with certain boundary conditions imposed at the asymptotic boundary. Okay. And once you have that, you have the explicit bulk to boundary propagator, and the Witten diagram technology just goes through. Good news, you don't have to deal with the singularity. You can compute Witten diagrams in this geometry, and they will respect all the Schwinger-Kelly rules. Okay. So any questions about this discussion? Okay, great. So now I want to say discuss two classes of problems, and I'll discuss a very general class of problems first, and then tell you where this class of problems came from. So we've taken to calling this geometry the gravitational Schwinger-Kelly geometry. So let me call it that. And let me invite you to study the following problem, where I have a probe field. I'll just write some action for the field. And sorry about my terminology, this probe is just a probe in the black hole. In this background, it's not the probe that I was coupling to my plasma. And let me talk about scalar fields for simplicity. I'll index them by an index m. And what I'm going to do is I'm going to stick in a factor here, which is not very covariant thing to do because I'm working in a particular coordinate choice. I'm going to modulate. So if m equals d plus 1, d minus 1, this is a minimally coupled scalar. But I invite you to study with me for a bit the general case, general m, and m I'm going to call the Markovianity index. You'll see why. For now, it's ad hoc. I just pulled something out of my hat. You see something nice about this construction? The thing that's nice about this is that this power of R allows me to modulate how the scalar interacts with the bulk metric between infinity and the horizon. So you can think of this as an effective dilaton, a non-dynamical dilaton. So you can think of this as something that's sitting in the class of Einstein dilaton theories, which have been studied in the context of ADS-CMT applications. And so let me just call this e to the chi. Chi is a non-dynamical dilaton. By which I mean that chi is not, there's no kinetic term for chi, but it has a radial profile, which I just postulate by hand. And the wave equation for this guy is actually quite simple in these terms of these derivatives that I've written down. And this wave equation we can solve, we can do various things with it and compute the Green's function for any m. But I introduced m for a reason, so let me tell you why I introduced m. And why did I chose to parameterize m the way I did? So m bigger than -1, the fields have no long-lived quasinormal modes. Okay, m equals -1 is marginal. It has logs, as you might expect. The modes are diffusive. In fact, I can even tell you what the effect of these modes is. These modes have a dispersion. Omega goes like -I k squared over the coefficient. It modulates the diffusion constant. It's a proxy for what the diffusion constant is. Different values of negative values of m give you different diffusion constants. Okay, we didn't cook this up. We didn't invent this for arbitrary reasons. We invented this because this is what gravity told us to do by studying two sets of problems. A Maxwell field in Schwarzschild ADS has m equals -d-3 or charge diffusion. So it's a longitudinal photons. And m equals -d-1 for vector polarized gravitons. Okay. So now let me explain that fact and then tell you why we went through this effort. Let's take Maxwell fields. Which is the problem that motivated Crossley, Glorioso, and Liu to study this geometry. But this was also studied by Jan de Boer, Michael Heller, and Natalia Pinzani-Fokiva around the same time. And the problem you want to study is just this. You want an effective action for this action, FAB. UG in the GRSK geometry. Now, what we can do is the standard thing that people do in this discussion. We can pick up, we can go to Fourier space on the boundary, and we can decompose the gauge field in the bulk in many ways. The standard thing to do is to work in radial gauge, which is what everybody does when that's what I would do when if I had to solve this problem a priori. Radial gauge does not respect Z2 involution. And you can try to fix it. The fixes are ugly. Okay. So, and there's a reason, which is the following. The radial component of Maxwell's equation is the radial Gauss's law. So if you're trying to think of ADS-CFT by doing radial evolution, the radial component is a constraint. It's just Gauss's constraint. If you now look at the equations on this two-sheeted geometry, the component of gauge field that goes around from one boundary to the other trivially is on shell. It's not off shell. Whereas the other modes are off shell because the radial gauge constraint has been put in. I mean, the Gauss law is just satisfied. So these folks decided to take that mode off shell by putting a source of charge on the horizon. And then they got various propagators as a function of what charge they put in. This seemed ad hoc to us, so we don't want to do that. So there's a much simpler solution. Forget about imposing a gauge constraint a priori. Work with gauge invariant variables, which would respect the Gauss constraint and would dictate what is happening under evolution. Big advantage, you get to abandon radial gauge, which means you can repurpose things with respect to this and use the Z2 involution without having to worry about the Z2 involution breaking your gauge condition. And a nice corollary, and this is something that's very well known to those of you who've studied quasinormal modes, but something that I had sort of forgotten, thanks to the way we worked out the discussion in fluid gravity, is that if you decompose the Maxwell field, there's a transverse and a longitudinal photon. This is vector polarizations of the photon, and this is scalar polarizations of the photon. And by scalar and vector, I mean with respect to the spin representations are correspond to in the space perpendicular to K. So you pick a direction. In the orthonormal space, I do rotations and I decompose my fluctuations into scalars, vectors, and tensors. Okay, so if I'm in 5 dimensions, I have 3-dimensional boundary. I pick the Z direction and then look at the XY plane and then decompose into scalars, vectors, and tensors with respect to that picked a degenerate example because now it's just SO2. And second payoff, at the quadratic level, these decouple in these two polarizations decouple. This also people are familiar with. This guy has no long-lived quasi-normal modes. But this does have the charge diffusion mode. Okay, this has m equals -d - 3. and this has m equals d minus 3. You can just check this. This is something that various of you might have seen before. And the same thing is true for gravitons. The tensor polarization of gravitons is a minimally coupled scalar. It has no long-lived modes. The vector polarization of gravitons is a shear modes, which come with m equals minus d minus 1. The scalar sector of gravitons has sound, and that has a polarization minus d minus 3. Okay, so big payoff in parameterizing the problem in terms of gauge invariance is that you get to decouple modes, which has a big advantage because now you can study. So if you just threw in a Maxwell field on the black hole, you will see that it sort of wants to, part of it wants to diffuse, part of it wants to decay and not diffuse. And you're left struggling with how to decouple the two. This parameterization does the decoupling. Second payoff, and I'll take maybe 2-3 minutes and then I can stop if that's okay. I'm slightly over time.
Okay. Please keep going.
The second payoff is this. The boundary conditions we want to impose are that we want to fix the sources of the currents on the boundary. So Dirichlet boundary conditions for the Maxwell fields or gravitons. But as I told you, the modes with long-lived quasinormal modes have non-local correlators. So if I try to integrate them out, I will get something non-local on the boundary. But gravity is very clever. It's much cleverer than we give it credit for, because by the time you go from this action to this action, and I emphasize this parameterization is ancient. This parameterization has been around for ever since the first days of any calculation in this problem. Surprisingly, nobody has tried computing actions in this parameterization. And I'll tell you amazing magic that happens if you actually compute actions. The Dirichlet boundary condition for gravitons and gauge fields immediately translates to Neumann boundary conditions whenever m becomes less than -1. Okay, you get exactly the right boundary terms to swap the boundary conditions. And this is important because if you see, the modes with m less than -1 are highly irrelevant near the boundary. So if you look at their near boundary expansion, they have non-normalizable modes that are growing. So if you try to freeze them, you can't. You won't get an onshell action that makes sense. However, if you quantize them with alternate boundary conditions by treating the conjugate momentum as the source, and then the field as itself as a corresponding wave, then you get an effective action. Except now you've done one Legendre transform, which means now the pole that was in the denominator now shifts the numerator, and you get a perfectly nice story. So gravity tells you what to compute. Gravity not only does this, and gravity says, the non-Markovian modes quantized with Neumann boundary conditions I mean, and I literally mean everything works out. Every counter term, everything just works out. It just descends on the nose. And what you should compute for, say, Maxwell fields is you compute Z boundary and sources for m greater than 0 for, let's say, Ketz and Brass. And waves for m less than 0 for Ketz and Brass. The nice thing is that along the way, these Green's functions, that there's something nice. Maybe I should say this in words and then stop. When you try to solve the wave equation for these non-Markovian modes, you will find that you can try to start out with a normalizable solution at leading order, because you're trying to solve this equation in powers of omega and k in gradient expansion. And you can try to solve it with the constant mode. But at next order, the power of m, if it's negative enough, it will give you a mode that diverges at infinity. If you try to compute its coefficient, the divergent mode, the coefficient is proportional to the dispersion relation. Okay, so this is, of course, this must be true because that's how you get the dispersion relation in the first place, by demanding normalizability of the solution. Okay, but what you see is that when the dispersion relation is satisfied, when the low-lying quasinormal mode goes on shell, you have a purely normalizable solution to this non-Markovian mode. That's the origin of non-locality. So what you want to do is keep that dispersion mode off shell. And the Legendre transform does that for you. Okay. I'm sorry for having gone over time, but let me give you the punchlines of what this is. So this has been computed for 2-point functions for arbitrary m. And in particular gives you the dynamics of charge diffusion and momentum diffusion for a neutral black hole. As expected, you get the correct answers, you get the correct dispersion relations, you get everything. But it also gives you the retarded correlator and fluctuation correlators. We've only computed 2-point functions. We are in the process of thinking about computing higher point functions. They can be done. I will leave you with two. So this is what's in the paper. There are a couple of things that are ongoing and hopefully should come out sometime soon. The story is a lot more interesting for Einstein-Maxwell theory, because then the momentum diffusion mode, which is in the vector sector, mixes with the longitudinal, with the transverse photon. So it's another mixing problem where you have a Markovian and a non-Markovian mode mixing. The mode B coupling can be done and studied. So this is what is work in progress with Loga and then Temple and Julio. And there's a similar story for the sound modes. As I said, it works pretty much the same way, with lots of confusions along the way, which I will spare you. So and you do get the right sound dispersion and the right correlators. So sometime in the hopefully not too distant future, there will be a story we can tell about how higher point functions associated with diffusion and sound are computed in these black hole backgrounds, and how the fluctuations associated with them are determined directly. Very good. So I think I am sorry for having gone over, but let me stop there and take questions.
Thanks, Mukund. It's very nice. It's better to go over time and go at this nice pace. Now there's time for questions. So please go ahead. Whomever wants to ask, yes. Don't be shy.
So yeah, let me ask a question. I cannot raise my hand. So now you said the story about the 2-point functions, like if you compute higher endpoint functions. During the talk, you said you looked at contact diagrams only. Is there like a problem if you look at non-contact diagrams, like for 4-point functions? So,
no, it's just not particular. I mean, no serious technical problem. I mean, just remember that if you want to do exchange diagrams, say you have a 3-point vertex, and you want to do scalar exchange, you just need a bulk-to-bulk propagator in addition to the bulk-to-boundary propagators.
yes.
But you can get them. So there's no obstacle to getting them. You can just get the bulk-to-bulk propagators as well. It's just suitably tedious in this problem. I mean, okay, so let me say it this way. The way we are doing the calculations, if we're trying to do them analytically, order by order in omega comma k expansion. So it just gets, there's no, mechanically, there's no problem doing the calculation. It just gets more and more tedious, and we've just been distracted trying to get the sound discussion working out. I do have a story with an undergraduate student who was working with me last year, where we can get the bulk-to-bulk propagators in special cases explicit. So no, I don't think there's a technical obstacle to it.
And so my second question is about the Z2 symmetry, which you kept, of course, in your problem, and so, or you exploited it. But is there a way that we can also think of, like in particular, like for far from equilibrium processes, like to break this Z2 symmetry, because it's like in kind of detailed balance symmetry, or?
Correct. Yeah,
so we can try to parameterize the breaking of the Z2 symmetry. And
well, there's a bigger problem than this is Z2, which is we need to know what the bulk geometry is. So let's say you do a quench, okay, which is a good example of this kind of problem. And then I want to understand what the real-time dynamics of the quench is for me to compute the. So I know what contour to draw in the boundary. I have some operator insertions. There might be non-analytic sources. It's all fine. What we know how to do is we know how to take a single copy Vaidya-like geometry and compute in it, or shockwave geometry and compute in it. And we need a prescription to upgrade that to a geometry of this kind. If you translate many things I said today, it is not explicit in any papers, you could say that as long as the quench is sufficiently adiabatic, it's sufficiently slow, and you stay close to the black hole equilibrium solution, you can basically do what we are saying. And this I think is also implicit in the MIT paper from a few years ago. They said this. But if you want to do a real fast quench, if you want to do something violent where things change rapidly, then I think we need a prescription for what the Lorentzian geometry is. So that's the problem I'm trying to solve. And I think once we solve that, there will be an effective Schwinger-Keldysh CP2-like symmetry on that geometry, which has nothing to do with this Z2. And there's a sort of Schwinger-Keldysh CPT in some sense because of this future boundary condition. Basically, it says that the way you think about Schwinger-Keldysh, you evolve the Kets to the future, Browse to the past. This guy is just what the initial state was. You can just replace the thermal state with some other initial state. But you have a future boundary condition which says at the future, Kets are identified with Browse. Or if I want to say it more fancily, I can say, you project against the maximally entangled state in the future. And so that's the boundary condition you should incorporate. And I don't know but I've been thinking about it. I don't yet have an answer for what the geometry must be.
Okay.
More questions?
Hi, Mukund. Pavel Kovton here. I would like to go to the picture at the very beginning of your talk that you gave of an open quantum system.
Yeah.
Right. The probe and the environment. And in normal statistical mechanics, this is the picture that is used, so to say, to derive the canonical ensemble from the microcanonical ensemble. Yeah. And then in what has been done so far in this holographic context is that, you know, we assume that the canonical ensemble is the right way to go, and we try to parameterize it using, you know, Schwinger-Keldysh or this complex geometry or whatnot. But of course, a more kind of satisfactory thing to do would be to derive the canonical ensemble, of course, under some assumptions about the density of states from this kind of picture that is on the screen now, so that the complexified geometry would be an emergent object. Mm-hmm. I was wondering if you had comments on that.
Yeah. So there is one. Okay. So let me say how I thought about the problem, and then I think what you're asking is it won't answer that, but I'll come back to answer your question. So I thought about the problem in the following sense. I thought someone gave me the state, gave me the thermally prepared Gibbs state, and I was supposed to Schwinger-Keldysh evolve it and compute correlators in it. So in that sense, then I can motivate. But you're right that if I start with this prototypical problem, then I should really think of trying to do more things by maybe understanding the microcanonical structure of the environment energy statistics, and seeing that in some windows high up on the spectrum, that microcanonical windows do give me effective thermal operators, which would be tantamount in this context to deriving ETH. Which, at least, if you translate the statement, it would be like saying, you do see eigenstate thermalization. The correlators do, microcanonical correlators are well approximated by thermal correlators. I don't have a good answer to your question, but I will point out that Don Merolf has a nice paper from maybe 2 years ago, trying to think about microcanonical geometries in the context of holography. Mm-hmm. This is, morally speaking, similar to the whole fuzzball story, but you want to talk about individual geometries associated with the microstates of the black hole. And you want to say that on average, in some energy window, those geometries give you answers that are close to thermal correlators. Of course, we don't in the fuzzball story, they have very powerful techniques and a lot of explicit solutions in the supersymmetric and near supersymmetric regime. What you're asking is sort of the exact opposite. You're asking high up on the spectrum for generic state, for generic high energy states. Mm-hmm. That we don't yet have an answer, but I think something like that is putting those kind of pieces together should tell us how to go about it.
Okay, yeah, thanks. Maybe a second shorter question is that you also mentioned about quantum fluctuations and the Hawking radiation.
Yeah.
So how would that be? I mean, I imagine this would be phrased in the standard language of quantum field theory in that geometry that you talked about.
Pretty much. I mean, this is exactly what Herzog and Sons said in their when they derived these, when the Sons-Starry-Nields prescription. So there's nothing really, I mean, I think novel and new in that. Mm-hmm. See, as you well appreciate, at the level of 2-point functions, getting the KMS condition is not a big deal. You can just go back to Euclidean and stick in the statistical factor. The non-trivial aspect in the problem is getting higher point functions and seeing all the statistics work. So that for the Markovian modes, I know how it works because that we've done, and we've shown that to be true. So, for example, there's one explicit calculation I know how to do that you can just look at. See, the annoying thing is that because the wave equation in these black hole backgrounds can't be solved analytically for generic momenta and frequency, we can do gradient expansion and then compare order by order in the gradient expansion. Of course, then you have to also expand the statistical factors, the omega factors you need to the beta omega, also in powers of omega. So you can check order by order in omega expansion that the KMS relations work for higher point functions. One case where you can do something very precise is you can look at it. You can do something precise, but I'll tell you it's a bit boring for reasons that are easy to say. Is ADS3 for the BTC black hole? You can just solve the wave equation. You can check everything. Bulk to boundary propagators are known. Bulk to bulk propagators are known. You can just compute the 3-point function and you see that this beautifully satisfied. There's some ratio of, there's some Maya G functions that satisfy everything you want. The 3-point function, however, in ADS3 is not super exciting because it's pretty much fixed by, even in the thermal state on the cylinder, it's fixed by conformal symmetry. So I think a slightly non-trivial thing would be to compute 4-point functions and see how the OP works out in this case, but that we have not done.
Okay, thank you. Yeah.
Good. Any more questions? As usual, I will stop the recording and then ask again if somebody wants to make comments. So first, let me thank you again, Mukund, for the very nice talk. And also let me say that we have a next talk on next Tuesday. Now I will stop the recording.